Hello friends, last class we discussed about the waveform synthesis and how to find the Laplace transform of few of the typical waveforms. Today's class we will see the two important theorems which we are going to use in network analysis and how to solve the electrical circuits using Laplace transform. So, the first important theorem which we are going to study in today's class is initial value theorem. This initial value theorem states that limit t tends to 0 f of t is equal to limit s tends to infinity s into f of s. If f of s is the Laplace transform of f of t, by knowing the expression for f of s, we can find the value of f of t at time t is equal to 0. So, this theorem states that limit t tends to 0 f of t is equal to limit s tends to infinity s into f of s. Now, let us prove this theorem. To prove this theorem, let us start with this expression. So, our aim is we are going to evaluate limit s tends to infinity integral 0 to infinity df by dt e power minus st dt. You know, if you look at this term, what is this term? This term is nothing but the definition of Laplace transform of function df by dt. Laplace transform of df by dt is limit 0 to infinity df by dt e power minus st dt. So, this is nothing but Laplace transform of df by dt. But we know Laplace transform of df by dt is s into f of s minus f of 0. Laplace transform of df by dt is nothing but s into f of s minus f of 0. So, limit s tends to infinity integral 0 to infinity df by dt into e power minus st dt can be written as limit s tends to infinity s into f of s minus f of 0. Now, let us just look at this LHS term. This left hand side we have the limit s tending to infinity and we have term with s, that is e power minus st. So, let me substitute this s is equal to infinity in this integration. If you substitute s is equal to infinity, what happens? This term becomes e power minus infinity. E power minus infinity is nothing but 0. So, when we substitute s tending to infinity in this integration, this function evaluates to 0. So, the left hand side of this expression is 0 when we substitute s is equal to infinity in this expression. So, I can write 0 is equal to limit s tends to infinity s into f of s minus f of 0. If you look at these two terms, this term is independent of s. So, I can take this term to other side of the equation. So, I can write f of 0 is equal to limit s tends to infinity s into f of s. I can write f of 0 is equal to limit s tends to infinity s into f of s. Now, what is this? Instead of f of t, I have in the place where normally we used to write t, f of t, I have 0. So, this term can be written as limit t tending to 0 f of t. So, this f of 0 can be written as limit t tending to 0 f of t. So, limit t tending to 0 f of t is nothing but limit s tending to infinity s into f of s. So, this theorem is called as initial value theorem, which is used to find the value of function at time t is equal to 0 by knowing the Laplace transform of any function. If you know the Laplace transform of function, Laplace transform of a function multiplied by s with where if you substitute limit s tending to infinity, you can find the initial value of the function. This theorem is called as initial value theorem. It is a very important theorem. So, just without even taking Laplace inverse, if you know the Laplace transform of any function, we can find the initial value of the function in time domain. Next theorem is the final value theorem. This final value theorem states that limit t tending to infinity f of t is equal to limit s tending to 0 s into f of s. Limit t tending to infinity f of t means it is the value of the function under steady state condition. It is the value of the function and at steady state condition, or you can call it as final value of the function. So, limit t tending to infinity f of t is equal to limit s tending to 0 s into f of s. Now, let us prove this theorem. To prove this theorem, let us again consider the Laplace transform of derivative of the function, but with limit s tending to 0. So, limit s tending to 0 integral 0 to infinity df by dt e power minus st dt. See, this is nothing but the Laplace transform of derivative of a function. This Laplace transform of derivative of a function is given by s into f of s minus f of 0. So, limit s tending to 0 integral 0 to infinity df by dt e power minus st dt can be written as limit s tending to 0 s into f of s minus f of 0. Now, let me substitute this limit, or let me substitute the value of s is equal to 0 in this integral. If I substitute this limit s is equal to 0 in the integral, what happens? It becomes e power 0, e power minus 0. E power 0, we all know it is 1. So, this integral reduces to integral 0 to infinity df by dt into dt, that is equal to, now we have the differential of the function and integral of the function. So, it results in the value of the function between the limits 0 to infinity. Instead of writing this way, this infinity I can write it as time t, where I can write time limit t tending to infinity. So, this expression can be written as limit t tending to infinity integral 0 to t df by dt into dt. What is this? This is the integral of a function, so it is the integral of a differential function. So, integral of differential function which results in the resultant value is just f of t between the limits 0 to t. So, this answer is f of t evaluated between the limits 0 to t. So, this function can be written as limit t tending to infinity f of t, which is nothing but the value of function at upper limit, minus f of 0, which is nothing but value of this function with lower limit. So, this term can be written as limit t tending to infinity f of t minus f of 0, that is equal to our RHS. On right hand side, we have the equation limit s tending to 0 s into f of s minus f of 0. If you look in this integral, this term f of 0 is independent of this limit t, and similarly on this side we have a term f of 0 again, which is independent of this limit s, this variable s. So, on this term can be split into two terms. One is limit t tending to infinity f of t minus f of 0, another one is limit s tending to 0 s into f of s minus f of 0. Since f of 0 is on both the sides of the equation, we can cancel it out. So, we can write limit t tending to infinity f of t is equal to limit s tending to 0 s into f of s. So, we have proved final value theorem. Final value theorem is used to evaluate the value of function at time t is equal to infinity by knowing the Laplace transform of this function f of t. If you know Laplace transform of this function as f of s, we say limit t tends to infinity f of t is limit s tending to 0 s into f of s. Now, let us try to see how do we solve the network equations using Laplace transform. To solve the network equations using Laplace transform, we follow certain steps. The first step is we describe the circuit with the help of differential equation. First step is we describe the network with the help of differential equations. Once you know the differential equation, we can take Laplace transform of the differential equation. If you take Laplace transform of the differential equation, the resultant equation is a algebraic equation in frequency domain. So, we can convert the differential equation in time domain to algebraic equation in frequency domain. And when we write the algebraic equation in frequency domain, that is by taking Laplace transform of the differential equation, we also incorporate all the initial conditions. So, we take care of even the initial conditions. Then once you write the Laplace transform, we manipulate the equations in S domain and try to get the Laplace inverse of the parameter which we are interested in. This is a procedure to be followed to solve the differential equations which describes the network. To start with, let us discuss or let us try to solve the networks with DC excitation. So, we will first concentrate on solution of networks with DC excitation. The first problem which we are going to consider here is a simple RC network with DC excitation. Now, here we have an RC network and there is a switch. The problem states that consider the series RC network and it is assumed that the switch K is closed at t is equal to 0. Find the current flowing through the network. So, our aim is to get the solution for I of t, current flowing through the network I of t. And it is given that the switch is closed at t is equal to 0. So, let us assume that the circuit is under equilibrium condition before the closing of switch, or in other words, I assume that this capacitor is an uncharged capacitor. This capacitor is uncharged capacitor. Now, let us see how to get the solution for the current flowing through this network. To find the current flowing through this network, let us try to describe this network with differential equation. Now, it is a single loop network. So, I can very easily write the equation for this network by applying Kirchhoff's voltage law. So, if I apply Kirchhoff's voltage law to this network at time t greater than 0, for time t greater than 0, we can write the supply voltage is equal to drop across this resistor plus the drop across the capacitor. What is the drop across the capacitor? Drop across the capacitor is 1 by C integral 0 to t I dt, whereas the drop across the resistor is R into I of t, which is equal to the supply voltage, which I can write as V into U of t, which is a constant supply voltage. We are considering DC excitation. So, the equation for this network is R into I of t plus 1 by C integral I dt is equal to V into U of t. So, this is the differential equation. Now, let us take Laplace transform of this equation. To write the Laplace transform of this equation, we must know what is the Laplace transform of 1 by C integral I dt. What is the Laplace transform of 1 by C integral I dt? We know Laplace transform of integral I dt is I of s by s plus q naught by s. Laplace transform of integral of I of t I dt is I of s by s plus q naught by s. So, Laplace transform of 1 by C integral I dt is I of s divided by Cs plus q naught by Cs. Again, I can combine this term q naught by C as the initial voltage across the capacitor, or voltage across the capacitor at time t is equal to 0. So, Laplace transform of 1 by C integral I dt is I of s by Cs plus V naught by s. So, this is the Laplace transform of 1 by C integral I dt. So, Laplace transform of 1 by C integral I dt is 1 by C into I of s by s plus q naught by s, and Laplace transform of the term R into I of t is R into I of s, and Laplace transform of V into U of t is V by s. So, this is the transformed equation. So, what we have done? We have translated this, we have transformed this differential equation into an algebraic equation, And in this problem we have assumed that the capacitor is uncharged. Since the capacitor is initially uncharged, I can substitute q of 0 as 0. So, if I substitute q of 0 as 0, this term vanishes. If this term vanishes, then we are left out with only one term, that is, this term is I of s divided by Cs. So, this term, the entire term reduces to I of s by Cs, and next we have a term R into I of s, that is equal to V by S. So, in both these terms I of s is common, so I can take out I of s. So, if I take I of s out, I can rewrite this equation as I of s into 1 by Cs plus R is equal to V by S. From this, by manipulating this equation, I can get the expression for I of s. So, I of s is equal to V by S into 1 by Cs plus R. Let me take this s term inside and divide the numerator and denominator by R. If I do the mathematical manipulation of taking this s term inside and divide the numerator and denominator by R, I can write the resultant equation for I of s as I of s is equal to V by R divided by S plus 1 by RC. V is a supply voltage, which is a constant. R is the value of resistor, which is a constant. So, we have a constant term in the numerator and a polynomial in S, and you can see that this is a first order polynomial in S. We have a first order term. So, we have a term I of s is V by R divided by S plus a constant. R is a constant, C is a constant. So, our resultant expression for I of s is a constant term given by V by R in the numerator divided by S plus 1 by RC. Now, we can, to find the expression for I of t, we know we need to take Laplace inverse of I of s. So, I of t is nothing but Laplace inverse of I of s, or it is Laplace inverse of V by R divided by S plus 1 by RC. Since V by R is constant, we can take this out, take this constant out. So, we can write it as I of t is equal to V by R into, we know the Laplace transform 1 by S plus A is e power minus at, but instead of A now we have 1 by RC. So, Laplace inverse of 1 by S plus 1 by RC is e power minus t by RC. So, the complete solution for current I of t for time t greater than 0 is given by I of t is equal to V by R e power minus t by RC. So, this is the expression for current flowing through a simple RC series network excited by a DC source, where we assume that the capacitor is uncharged. Now, let us consider another example. It is a RL network. Let us try to find the current flowing through the RL network. So, let me read out. Consider a series RL network as shown in figure. It is assumed that the switch K is closed at t is equal to 0. Find the current flowing through the network, and this is the network given. As I told you already, we are trying to solve networks with DC excitation. So, the network has a DC source with these polarities. There is a switch in this network, and a resistor and an inductor are connected in series. Since it is a single loop network, I can very easily write the equation describing this network with the help of Kirchhoff's voltage law. So, by applying Kirchhoff's voltage law, I can write the equation for this network as R into I, that is the drop across the resistor, plus L into di by dt, that is the voltage drop across the inductor, is equal to the supply voltage. Or I can write R into I plus L into di by dt is equal to V into u of t. Now, this is a differential equation which describes the circuit. Now, let us try to find the Laplace transform of this equation. To find the Laplace transform of this equation, we must know what is the Laplace transform of L di by dt. How do we find the Laplace transform of L di by dt? We know Laplace transform of di by dt is given by s into I of s minus I of 0. I of 0 is the initial value of current. So, Laplace transform of L into di by dt is L into s into I of s minus I of 0. So, this is the Laplace transform of L into di by dt. Laplace transform L di by dt is L into s into I of s minus I of 0. So, if I take Laplace transform of this equation, the Laplace transform L di by dt transforms to L into s into I of s minus I of 0. What is I of 0? I of 0 is the initial value of current flowing through the inductor, plus Laplace transform of R into I of t transforms to R into I of s, and Laplace transform of V u of t transforms to V by s. Now, let us apply the initial condition, that is the initial value of current flowing through the inductor. Let us since the circuit is closed only at t is equal to 0, the circuit excitation is given to the circuit only at t is equal to 0, there is no current flowing through the inductor before the closing of switch. So, I of 0 is 0. So, I of 0 is 0. So, can substitute I of 0 is equal to 0. If I substitute I of 0 is equal to 0, thus Laplace transform L di by dt reduces to Ls into I of s. So, Laplace transform of L di by dt reduces to Ls I of s, and we have the term R into I of s. Since I of s is common in both these terms, I can rewrite this equation as Ls plus R into I of s, Ls plus R whole thing into I of s is equal to V by s. So, what is I of s? I of s is equal to V by s into Ls plus R. So, I of s is V divided by s into Ls plus R. Now, let me divide this numerator and denominator by L. If I divide the numerator and denominator of this term by L, I can write I of s is equal to V by L divided by s into s plus R by L. Now, how do I get I of t? I of t we can get by taking Laplace inverse of I of s. But if you will see this term, we do not know what is the Laplace inverse of this particular expression. We know what is the Laplace transform of Laplace inverse of 1 by s. We know what is the Laplace inverse of 1 by s plus a or s plus a constant, but we do not know what is the Laplace inverse of a term where you have a constant divided by s into s plus a constant. V by L is a constant, R by L is a constant. So, how do I take the Laplace inverse? So, I must rewrite this term I of s in such a way so that we can find the Laplace, we can take Laplace inverse of the resultant term. This can be achieved by applying partial fraction expansion for I of s. So, I of s which is given by V by L divided by s into s plus R by L can be written as some constant a. It can be written as a by s plus b divided by s plus R by L. If I evaluate the value of a and b, I can find the Laplace inverse of these two terms. I can very easily find the Laplace inverse. Laplace inverse of a constant by s, we know it is a into u of t. Laplace inverse of b divided by s plus R by L is nothing but b e power minus R by L into t, e power minus R by L into t. So, we can find the Laplace inverse of the term I of s if we bring this I of s term to this form, that is a by s plus b divided by s plus R by L. So, I need to evaluate a and b. This a and b can be evaluated by applying partial fraction expansion. So, let us say how do we evaluate this term. So, we have the expression I of s is equal to V by L divided by S into S plus R by L. We have the expression V by L divided by S into S plus R by L. This term we have written it as A by S plus B divided by S plus R by L. To evaluate this constant A, multiply I of s term with the denominator of A, that is multiply this term by S and substitute S is equal to 0. To evaluate A, we multiply this I of s term. You can easily find the value of A by multiplying I of s term with S and substituting S is equal to 0. If I do this manipulation, I of s is V by L divided by S into S plus R by L. Let me multiply this term with S and substitute S is equal to 0. When I multiply this term with S, S and S gets cancelled. Let me substitute S is equal to 0. The numerator I have the term V by L. In the denominator, when I substitute S is equal to 0, this reduces to, denominator reduces to R by L. So, L and L gets cancelled. So, I can say the value of A is V by L. Value of A is V by L. Similarly, to evaluate B, to find the value of B, multiply this I of s expression by the denominator of B, and substitute S is equal to minus R by L. To evaluate the value of B, multiply I of s expression by the denominator of B term, which is nothing but S plus R by L, and substitute S is equal to minus R by L. So, if I do this I of s term multiplied by the denominator of B term gives me V by L by S. This is I of s multiplied by S plus R by L, and we need to substitute S is equal to minus R by L. Need to substitute S is equal to minus R by L. So, if I substitute S is equal to minus R by L, the term B becomes V by L divided by minus R by L, or it becomes minus V by R. This minus V by R. So, this term, this A reduces to, sorry, there is a small mistake, it is V by R, and B is equal to minus V by R. So, we can take this V by R outside. V by R, remember this term is not L, this is R. Because A value is V by R, B value is minus V by R, and hence this term becomes V by R into 1 by S minus 1 by e power minus R by L. So, I of t is V by R into Laplace inverse of 1 by S, that is 1, and Laplace inverse of 1 divided by S plus R by L, which comes out to be e power minus R by L into t. So, the expression for I of t is V by R into 1 minus e power minus R by L into t. Now, so we have seen what is the expression for current flowing through a RC circuit excited by DC value, and we have also seen what is the expression for current flowing through an RL circuit. Now, let us try to get the current flowing through an RLC network. So, your aim is to find the expression for current I of t for a RLC circuit shown. Again, here to make our problem simple, let us first assume the circuit with 0 initial conditions. Later on we will take up problems with some initial value of current through the inductor and initial value of voltage across a capacitor. Now, let us derive the expression for current I of t for a series RLC circuit. We assume 0 initial conditions for the inductor current and capacitor voltage. So, this is the circuit under consideration. We have a DC source with constant voltage V, a switch which is closed at time t is equal to 0, and a resistor, inductor and capacitor connected in series. When I close the switch at time t is equal to 0, and if I write the equation for the circuit by applying Kirchhoff's voltage law, we can write the equation for this circuit as the supply voltage V is equal to drop across the resistor plus voltage drop across the inductor plus voltage drop across the capacitor. So, you can write V is equal to R into I plus L into di by dt plus 1 by C integral I dt. Now, let me take the Laplace transform of this equation. So, you can write the transformed equation as I of s is equal to I of s into R, that is R into I of s plus Ls into I of s plus 1 by C into I of s is equal to V by S, because we have assumed that there is no current flowing through the inductor before time t is equal to 0. The initial value of current flowing through the inductor is 0. Similarly, we have assumed that the capacitor is an uncharged capacitor. So, neglecting initial conditions, we can write the transformed equation as I of s is equal to R plus Ls plus 1 by Cs, which is equal to V by S. Now, this equation can be rewritten in this form. So, keeping I of s on one side, let me take all other terms to other side. We take all other terms to other side and do some mathematical manipulation. This term I of s can be written as V by L in the numerator divided by S square plus R by L into S plus 1 by LC. If I just rewrite, I can bring I of s to this form just by bringing this term to denominator and multiplying every term by s and dividing this numerator equation and denominator equation by L. So, you can write this equation as V by L divided by S square plus R by L into S plus 1 by LC. V by L is a constant, so you can take it out, and this equation can be written as 1 by S square plus R by L into S plus 1 by LC. See, if you look at this equation I of s expression, and if you compare the I of s expression which we got in the previous two problems, we could see that I of s equation here is in the RC circuit was a first order equation. Now, here we have got a second order equation. This is a second order equation. We have got a second order equation in S. Now, to find the Laplace inverse of this term, we need to bring this term to the term where we can take Laplace inverse. So, to bring this term to Laplace inverse, I can factorize this second order equation. If you factorize the second order equation, you can factorize it into two first order terms. Let us say the one root of this equation is S1 and another root of this equation is S2. So, this second order equation can be written in this form: V by L into 1 divided by S minus S1 into S minus S2. You can write in this form. Now, what is S1 and S2? S1 and S2 are the roots of this second order equation. This is of the form S square plus Bs plus C, A square plus Bs plus C. If the equation is of the form A square plus Bs plus C, we can get the roots of this equation by applying the form. It is minus b plus or minus root of b square minus 4ac divided by 2a. So, if you apply this form, we can get the equation or get the roots of this equation as minus r by 2l plus or minus root of r by 2l whole square minus 1 by LC. So, the roots of the second order equation can be written as minus r by 2l plus or minus root of r by 2l whole square minus 1 by LC. Now, depending on the term under this root, we can have different types of roots. So, let us say the term under the square root is positive. The term under the square root is positive. If the term under the square root is positive, I can easily find I can evaluate this evaluate this square root term, which comes out to be a real term. It comes out to be a real term. So, if it comes out to be a real term, one root S1 is minus r by 2l plus the real term, and another root is minus r by 2l minus this real term. So, we will get two roots which are real and distinct. So, case 1 is if the term under the square root is positive, we get real and distinct roots, that is S1 and S2 are real and they are different, they are not equal. So, the roots can be real and distinct. So, the first case is we assume that the roots are real and distinct. If the roots are real and distinct, then the expression for I of s is v by L into 1 by s minus s1 into s minus s2. So, now even if I know the value of s1 and s2, s1 will be a real constant, s2 is another real constant. So, let us assume that s1 value is something equal to a and s2 value is equal to b. If s1 value or s1 is a real constant and s2 is also a real constant. So, now our aim is to bring this I of s term to the form where we can take Laplace inverse. So, I of s is of the form v by L into 1 by s minus s1, s1 is a real constant, into s minus s2, s2 is also a real constant. Since I cannot directly take Laplace inverse of this term, let me apply partial fraction expansion, so that I can write I of s as v by L into a divided by s minus s1, or this term I can write as a divided by s minus s1 divided by b divided by s minus s2. As I told you in the previous example, to evaluate a, multiply this I of s expression by the denominator of a and substitute s is equal to s1. So, to find a, multiply I of s term with s minus s1 and substitute s is equal to s1. So, if I do this manipulation, I can write, the moment I multiply this by s minus s1, my I of s into s minus s1 reduces to v by L into 1 by s minus s2, and I need to substitute s is equal to s1. So, this manipulation gives me the value of a. To evaluate a, I need to multiply I of s expression by s minus s1 and substitute s is equal to s1. So, a value is v by L into 1 divided by s minus s1, where s should be replaced by s1. So, the constant a is v by L into 1 by s1 minus s2. This is the value of a, v by L into 1 by s1 minus s2. In a similar way, to find the value of b, multiply I of s expression divided by s minus s2 and substitute s is equal to s2. If you do that manipulation, again you will find b value is minus of v by L into 1 by s minus s1. So, since I know the value of a is v by L s minus s1 and b value is v by a minus of v by L s minus s1, I can take out this term outside. So, I can write I of s is equal to v divided by L into s1 minus s2 multiplied by 1 by s minus s1, because we have taken a outside and b also outside. A and b are equal with, but they have opposite sign, equal in magnitude, but they have opposite sign. So, I could take this term v by L into s minus s1 minus s2 outside. So, I can write v of s is equal to I of s is equal to v by L into s1 minus s2 multiplied by 1 by s minus s1 minus 1 by s minus s2. What is s1? s1 is minus r by 2L plus this term, and s2 is minus r by 2L minus this term. So, these two roots are not equal, s1 is not equal to s2, but they are real roots. So, I of t can be written as v by L into s1 minus s2 into Laplace inverse of this term. Laplace inverse of this term, we know it is equal to e power s1t minus Laplace inverse of this term, that is 1 by s minus s2, which is nothing but e power s2t. So, the solution for I of t for time t greater than 0 for a circuit with R, L, C values in such a way that the term under this root, that is r by 2L square minus 1 by LC, if it is a real number, then I of t is given by v by L into s1 minus s2 e power minus s1t minus e power minus s2t. Now, if the term under this root is 0, that is r by 2L square is equal to 1 by LC. R by 2L square, if it is equal to 1 by LC, the term under the root becomes 0. In that case, both the roots are real roots, but they are equal. Both the roots take the value minus r by 2L. So, we may have a case the r, LC values are in such a way that the term under this root may become 0. In that case, let us see how do we get the expression for current I of t. So, the second case is the roots are real, but they are equal, that is S1 is equal to S2. If S1 is equal to S2, the expression for current I of S reduces to V by L into 1 by S minus S1 into S minus S1, or I can write as V by L into 1 by S minus S1 whole square, 1 by S minus S1 whole square. So, now this equation is very simple. It is in a form where we can easily take Laplace inverse. This is of the form 1 by S minus A whole square. If it is 1 by S minus A whole square, we know the Laplace inverse is t e power a t u of t. So, Laplace inverse of this term is I of t, which is equal to V by L into t e power S1 t u of t. See the solution of I of t. If the roots are real and distinct, I of t expression is the difference between two exponential terms. And see here, this S1 has a negative real part, minus r by 2L. It is a minus r by 2L. So, if you substitute S1 is equal to minus r by 2L into this real number, then it comes out to be an exponentially decaying term. Again, this happens to be an exponentially decaying term. Same thing here, you will have S1 as such has a negative, S1 is minus r by 2L in this case, minus r by 2L. So, it comes out to be a negative term. So, this is the expression for I of t. Now, the third case, if you see the term under the square root may be negative. If the term under the square root happens to be negative, then square root of a negative term results in imaginary term. The square root under this term results in imaginary term. So, we have three cases where the term under square root is real and positive, and next case we took the term under the square root is 0. Now, we are considering a case where the term under the square root is negative. If the term under the square root is negative and we take the square root operation, it results in an imaginary term of value, it is an imaginary term. So, the root will have the roots of the second order equation will have a real part and an imaginary part, or I can write the roots S1 and S2 in complex form, which is equal to minus alpha plus or minus j omega. What is alpha? Alpha is r by 2l, and omega is the square root of this term with a negative sign, square root of this term with a square root of the term under the root with negative sign. So, the roots will be of the form minus alpha plus or minus j omega. So, let me substitute these roots. So, instead of S1 and S2, now S1 is minus alpha plus j omega and S2 is minus alpha minus j omega. So, if you substitute these roots in I of s expression, I of s is equal to V by L into 1 divided by S plus alpha plus j omega, that is the first root, and the second root is minus alpha minus j omega. So, if I substitute, the second term can be written as S plus alpha minus j omega. So, if you look at this denominators, this S plus alpha plus j omega, this is S plus alpha minus j omega. This S plus alpha, let me view it as term A and j omega as term B. So, I can view this term as A plus B. If we view this term as A plus B, this term is A minus B. So, in the denominator we have the term A plus B into A minus B. So, I can write it as A square minus B square. What is B? B is j omega. So, B square itself is j square times omega square. J square is again minus 1. So, if I multiply these two terms, it results in A square plus B square, or it is S plus alpha square into omega square. So, now the expression for I of s is V by L into 1 divided by S plus alpha whole square plus omega square. Now, how do we take the Laplace inverse? To take the Laplace inverse, I know the Laplace inverse of A by S plus A whole square plus omega square is e power minus at sin omega t. So, to bring it to the standard form, let me multiply the numerator and denominator by the term omega. So, if you multiply the numerator and denominator by omega, I can write I of s is equal to V by L into omega divided by S plus alpha whole square plus omega square. Now, I can very easily find the Laplace inverse of this term. Laplace inverse of this term is e power minus alpha t sin omega t into u of t. So, the solution of current I of t is V by L into omega into e power minus alpha t sin omega t. So, to conclude, if you have a series RLC circuit, the resultant expression for current depends on the nature of the roots of the denominator polynomial of I of s. So, the roots can be real and distinct. If the roots are real and distinct, the resultant solution for I of t is given by two exponentially decaying wave, or it can be an exponentially decaying wave multiplied by a ramp, or it can be an exponentially decaying wave multiplied by a sinusoidal wave. So, depending on the value of RLC, we get the expression for I of t. Tomorrow's class we will take some more example with numerical values, and we will see how to analyze the circuits with AC excitation. Thank you.